Greetings, KAUST community and honored guests. I hope you're enjoying week 2 of winter enrichment, anywhere near as much as I am. I would especially like to recognize our visitors, our visiting undergraduates from the Saudi Initiatives program and from the poster session program. If you are here under either of those auspices, could you rise right now so we could recognize you? Saudi Initiative and our poster undergrads. Thank you. By bringing your scientific endeavors in sustainable technologies and other areas related to KAUST's mission to our campus, you're helping us to fulfill the motto that we've chosen for this year's enrichment program. In Latin, alios ditans, homo ditatur. In enriching others, one is enriched. I understand that a computer system outage at Jeddah Airport stranded a number of you Friday evening, and I hope that you have recovered on your sleep cycles well enough to enjoy tonight's keynote. Our apologies for that rough beginning to what will be a glorious week on the shores of the Red Sea, in the presence of minds assembled from around the world. Actually, I have full confidence that you'll be able to stay awake for tonight's speaker. We spoke last week when we opened WEP about how what we learn about our origins can add to our own sense of place in the universe. This includes knowledge of our intellectual origins in our disciplines, of our cultural origins, our genetic origins, and our physical origins. We learned a significant amount last week in the first 3 categories, notably from Lele Neme, an archaeologist, from Svante Pabo, the human geneticist, and as well from our CEO, Lubna Olian, who reflected on what our social and economic culture owes to academic centers of excellence. We also learned last week about limits and stretching them and how they are often estimated incorrectly, on the low side that is, by experts, and we can thank for this gift our free diver champion, Guillaume Neret. Tonight we get a double dose on origins and on the pushing back of limits in the lecture of Tony Readhead. Back to the beginning in cosmology and radio astronomy. Please allow me to tell you a little bit about Tony before I give him this podium. Professor Anthony C. Readhead, a physicist, mathematician, and astronomer, is the Robinson Professor of Astronomy at Caltech, a senior research scientist at NASA's Jet Propulsion Laboratory, and the director of the Owens Valley Radio Observatory in Southern California. Like many people at KAUST, he has become an instrument maker in order to carry out his research. It's just that his instruments are usually much larger than ours for observations in cosmology, particularly the cosmic background radiation and active galaxies. And tonight's lecture is the first of 2 that we will have from Tony this week. You may come back Tuesday at 12:30 for a brown bag lecture on the mysteries of black holes. Tony was born and grew up in South Africa, earned his PhD at the renowned Cavendish Laboratory in Cambridge University, and began his long and distinguished career at Caltech in 1974 as a postdoc. Well, the rest is history, and you can read the details online. In 1995, he was elected to the U.S. National Academy of Sciences. And now to origins.
Thank you very much, David. It's a great pleasure and privilege to be here. I have this opportunity to talk to you tonight. And it's my first visit to KAUST and my first visit to Saudi Arabia, and I'm completely blown away by what I've seen. It's truly a fantastic institution you have here. And I think it's both beautiful and it has tremendous potential, which it's realizing very fast. So it's a very exciting place to visit, and I do thank you for inviting me to give this lecture tonight. So tonight I want to tell you about recent work on the origin of the universe, and I'm going to be talking about this figure that you see here, and I'll explain it a little bit. Is the audio a bit too loud, or is that okay? It's okay? Okay, great. So I'll explain it as I go through, but there are several messages that I want to try to get across several things I really want to tell you about. One of them David's already alluded to, which is the interaction between instrumentation and observation and theory. And so we'll be talking about that quite a bit. Another you will see is that cosmology really proceeds by fits and starts, like many fields. There'll be a tremendous, spurt of development and growth, and then there can be many decades or even centuries of more or less stagnant. And we'll be talking today about the sort of huge spurt of growth that happened in the beginning of the 20th century when Einstein published the general theory of relativity in 1916, and 13 years later, Hubble discovered the expansion of the universe. Fantastic developments suddenly changed our view of the universe completely. But oddly enough, even though astronomers and cosmologists were pouring their energy into this field, from 1929 till about 1999, very little progress was made, and there were even papers being written about how several things that people were trying to measure just couldn't be measured, and it was looking pretty hopeless. But in the mid-90s, things really started to pick up, actually sort of late 80s, mid-90s. And in the last 15 years now, there's been a huge growth and development in cosmology. So I want to tell you about that, but it's been very interesting, and I'd like to give you a feel for what it takes to build up to that sort of progress. Okay, so this figure here, let's just see if this will... this is a signal from 380,000 years after the Big Bang. So it's a signal that was emitted 13.8 billion years ago. And theorists started predicting this kind of curve. That red curve you see there is a theoretical prediction. And when they started predicting this, most of us in the field of observing thought, well, what do they know about what was going on 380,000 years after the Big Bang? Turns out, astonishingly, the theorists really did get it right. The fit, as you can see, the blue points there are data from the Planck satellite, which is still flying as I speak, and it's a beautiful fit to the data. And this model has only 6 free parameters, so anybody who's done any kind of data analysis like this will realize that this is very, very tightly constrained. But those 6 free parameters are very interesting parameters, because one of them tells us how much density in ordinary matter there is in the universe, the stuff that we're made of, protons and neutrons. That's one of the parameters that comes out of this. Another, it tells us how much energy there is in dark matter, and I'll be talking about the dark matter. It also tells us how much energy there is in dark energy. So it tells us the 3 major energy constituents in the universe. And then it also tells us about the slope of the spectrum of fluctuations that were produced in the very early universe in an era called inflation, right at the beginning. In fact, the Big Bang itself. And then there's a couple of other parameters that are a little bit more esoteric that we won't have to worry about. But basically, it's telling us these fundamental parameters of the universe in a very, very accurate way. So we're now in the era of precision cosmology, and I will show you the experiment that launched us into the era of precision cosmology a little later. It was a beautiful experiment called Boomerang back in 2000. Okay, but now, so I'll tell you more about this as we go through. But just last March, March the 17th, another figure was published by this group called Bicep 2. And some of you may have seen there's been a tremendous amount of discussion about this in the literature. Because they've seen, they think, this signal down here, and this paper is a very, very good paper. It's absolutely beautiful paper, no doubt about that. Is it a masterpiece? We don't know yet, for reasons I will tell you, but I'm asking, is it a masterpiece in the sense that they've actually discovered something fundamentally new about the universe? We don't know that yet, but their hope is that this part of the signal here, you see they've measured these points here, and then there's a sort of little bump here that's fitting this dashed curve. That dashed curve, if it exists, is caused by the Big Bang itself. It's basically what happens in the first trillionth of a trillionth of a trillionth of a second of the life of the universe. 10 to the minus 36 seconds. So here we're talking about 380,000 years. Here we're talking about 10 to the minus 36 seconds. And that's why this is thought to be so interesting and so important. Now, if I was giving this talk before March the 17th of last year, that is before these points existed, what I would have been doing is telling you about the 4 experiments I've been involved in: the Cosmic Background Imager, DAISY, Quiet Q, and Quiet W, all of which put points in this part of the curve. But clearly, this sensitivity here is much better than we've achieved, and so I'm not going to tell you about these upper limits here. I'm going to talk about these actual points themselves down here. But I will be talking about the CBI and Quiet Q and Quiet W to give you a sense, a flavor of what it's like to work in the field. So the question is this a masterpiece? Have they really detected something from the first trillionth of a trillionth of a trillionth of a second in the life of the universe? We don't know, and the reason that we don't know is because of this beautiful galaxy that we live in. And it's possible that what they've detected is simply dust in the galaxy. So we don't know whether this very sensitive experiment, like looking out of an automobile, has been corrupted by dust and dirt on the windscreen, or whether they've actually looked back 13.8 billion years to the Big Bang itself. So this has been a question I've had for the last 15 years working in the field, is can any direct signal from the Big Bang itself be measured from our location in the galaxy, or are our observations corrupted by all this dust and stars that we have to look through before we see the very early universe? Well, now I want to talk about the pioneering era in radio astronomy, because I feel that we've now entered an era like that again in radio astronomy. I'll be talking about it again at the end of the talk, but already you'll see from the potential importance of the work I've just discussed, it looks like we've entered one of these eras of major discoveries in cosmology. So let's look back at the last major burst of discoveries in radio astronomy. And the pioneering era of radio astronomy culminated in the 60s with 4 major discoveries. The first was in 1962. Scott and Ryle published a paper which gave compelling evidence of an evolving universe. There was a lot of interest at that time in the steady state theory of the universe, which said the universe had always been the same as it was today, and that it existed eternally, and that nothing changed on large scales in the universe, the steady state theory. But what they found was, as they looked further back, as they looked to more and more distant, greater and greater distances, they were counting more and more quasars. And that showed there were many more quasars in the past than there are today. So it showed that the universe was evolving. So this was the first nail in the coffin of the steady state theory. And then there were the 3C catalogs, which the Cambridge 3Cs for Cambridge, they made this catalog of the radio sources in the sky. And Cyril Hazard, who wasn't at Cambridge, very accurately measured the position of one of these sources, 3C279, and sent it to Martin Schmidt at Palomar Observatory. And Martin Schmidt got an optical spectrum of it and found that this object was at a very, very large distance, at a cosmological distance. It was very exciting because it was one of the brightest objects in the sky, but it was found to be at a cosmological distance, which clearly then suggested that most of the other radio objects they were looking at were at these very large distances. And that meant that it was more evidence for an evolving universe, because these objects were at large distances but not nearby us, none of them near us. But also, almost immediately, physicists Donald and Mel at Cambridge suggested the only thing that could possibly produce the amount of energy these things were showing was a supermassive black hole. And we now know that's true, and I'll be talking about that on Tuesday, how we know there are supermassive black holes in these objects. And then in 1965, the microwave background radiation was discovered by Penzias and Wilson. And I'll be talking a lot about that today. And then in February 1968, Tony Hewish and Jocelyn Bell discovered pulsars. They published the paper in February 1968. In fact, I was so excited by this paper. I was an undergraduate. I'm just finishing my undergraduate in South Africa. I was applying to Cambridge, and I switched my application from optical to radio astronomy, went to Cambridge, and Tony Hewish was my advisor, an absolutely fantastic advisor. The important thing about pulsars is not only did they tell us a lot about astrophysics, but also they showed that very dense, very, very dense states of matter exist in nature. Pulsars are neutron stars, and up until then, people had talked about neutron stars, but they never knew whether these really dense states of matter actually existed in the universe, and suddenly here was evidence for them. And they're all over the place, all over the galaxy, lots of them. That was very important because it brought dense states of matter. Of course, once you've got neutron stars, you can go the step further and think of black holes. And basically, it brought very dense states of matter. In particular, it brought black holes into the scientific arena. It was now respectable to talk about black holes. Before that, people thought it was a little bit science fiction, and they weren't sure it was that respectable. So that was all very exciting. These are all, of course, obviously zero-thoughted discoveries, I would say. They're all masterpieces. And you can say, well, how was it radio astronomy did so well? Well, clearly, one thing is raw talent. That's obviously a major factor. There are 4 Nobel Prize winners up here. Okay? But another thing that was very important, what we referred to at the beginning and what David referred to, very close synergy between technical development and science over the whole range of relevant technologies. That's really how this happened. And radio astronomy has always proceeded this way. Very strong links between theory, observation, development of instrumentation. That's its major strength. So I really like this designation that these are all masterpieces because when one thinks of masterpieces, one tends to be thinking of the arts rather than the sciences, but I think there's so much similarity between arts and sciences. And basically, it's a question of creativity. What does it take to produce a masterpiece? What does it take to be really creative in either the arts or the sciences? And there are not that many discussions of this by people who are really creative artists in any literature as far as I know. Very few. But the one that I've found and that I like the most is this one, A Room of One's Own by Virginia Woolf. And she gave this 2 talks in Cambridge at Newnham and at Girton College back in October 1928. And she was actually talking about the role of women in writing literature. And she was saying, what does it take? What would it take to create the conditions that would enable women to reach their full potential as creative artists? But she goes far beyond that, and she asks the much broader question of what does it take for anybody to reach their full potential? And so it's a very interesting discussion, and I read it often, and I always learn more. And when I teach at Caltech, whether I'm teaching radiative processes in astrophysics or cosmology or high-energy astrophysics or radio astronomical instrumentation, I always tell my students there's one book they have to read. They've got one set book, and this is the book they have to read. And my favorite quote from this book is this: "For masterpieces are not single and solitary births. They are the outcome of many years of thinking in common, of thinking by the body of the people, so that the experience of the mass is behind the single voice." And you might wonder, well, who is she talking about when she says that? What sort of masterpieces is she talking about? Well, she's talking about none other than William Shakespeare. And then when you think about it for a moment, you think about the precedents William Shakespeare had that enabled him to write his work. Of course, this is only a tiny fraction of them, but the names just come tumbling out. So I think it's really important when you're trying to think of creativity to give due thought to all the conditions in society that enable one to be creative. It's amazing to be in a society that allows us to do art or do science. And there's a huge amount of infrastructure that makes this possible. And we should never forget that. And I was walking around your museum here earlier this afternoon, and I saw exactly this sentiment expressed in different words. I was very delighted to see that. So the scientific method and modern technology enable us to study the evolution of the universe by direct observation. That's a wonderful thing, and hence lead directly to modern cosmology. Now, of course, ancient cultures developed cosmology but didn't have the advantage of all the instruments that we have, so they only had varying degrees of success. This is Anaximander's cosmology in 550 BC. He thought the Earth was surrounded by a ring of clouds, and outside that ring of clouds was a ring of fire, and there were holes through these clouds that enabled the radiation to get through, from the fire to get through, and this is what the sun and the moon was, etc., etc. So, it fitted some of the facts, but not a very successful cosmology. The most successful cosmology in the ancient world was Aristotle's cosmology, where you have a spherical Earth in the center of a spherical universe. And this dominated Western thought for 1800 years. Now, astronomy is the most ancient of sciences, and Islamic astronomers played a critical role in the development of astronomy. For many centuries, they were the leading astronomers and cosmologists in the world. And obviously, I think you all know this, but for this reason, of course, most of the bright stars in the night sky have Arabic names. If you look at Orion, for example, of the brightest stars, there's only one which has a Greek name. All of the others are Arabic names. And that's true for all the constellations in the sky. And here's the belt of Orion. You can see him when you walk out tonight. You'll see him brightly, almost directly overhead. And we're going to, in the sword of Orion, the little middle one here is the great nebula in Orion. And on a very dark night, you can see it with the naked eye, and you can see it very easily with a small telescope or a pair of binoculars. Now, the ancient Greek astronomers noticed an extraordinary phenomenon, and I'm going to go over some of this early cosmology because of the way it relates to later cosmology. Some of the planets, the wanderers, went backwards some of the time. And that's not allowed, of course, by Aristotle's model, because you're only allowed to, all of those spheres had to rotate at constant speed. There's no way you could get a planet going backwards on Aristotle's cosmology. And so therefore, Aristotle's cosmology needed to be fixed. And so this just shows you starting in, I guess it's October 1996, Mars is up there, and you see the constellations here, and then a day-by-day measure of where Mars is, and this is what it does over the next 9 months or so. It goes backwards. So that's the problem that they had to solve. Okay, so Ptolemy, his magnum opus, the Almagest, it's an Arabic name that's been given to this great work, and that's in recognition of the fact that were it not for all the wonderful work that was done by the Arab astronomers and cosmologists over the next 1,000 years, we would never have got the Almagest. That was completed about 150 AD. And he worked on motion of heavenly bodies using a system of epicycles. And that was founded on the hypothesis that all celestial motions were circular. So this is Aristotle's hypothesis. The Earth is at the center. Sorry, not Aristotle, Ptolemy's. The Earth is at the center, and Mars and other planets move around on a circle with a circle called an epicycle going around it. So you can easily see how you could go backwards if you had something like that. So the great Islamic contributions to astronomy and mathematics, and this is only a tiny fraction of them that I'm putting up here. But of course, there's the great work by Khwarizmi, and there's a building here named after him. Of course, he published this first work of algebra, and he also introduced the Indian number system and the concept of zero, and did a lot of other things as well. Al-Khujandi developed a very accurate mural sextant to measure the tilt of the Earth's axis relative to its orbital plane. He actually made astronomical measurements with an accuracy of arc seconds, which is truly phenomenal. And he measured this angle between the Earth's axis and the orbital plane to within about a 20th of a degree, which is a phenomenal feat. The modern value is given here. His value is here. And at the time, you can see that the Indians and Ptolemy were way off compared to Al-Khujandi. And he went on to be important in developing some of these instruments. And then I really like this, which I discovered this afternoon in the museum. Al-Haytham, also known by this Latinized name Al-Hazan, because I had always thought that Francis Bacon was the founder of the scientific method. That's what I was taught and what I always told people. But I went and read this, and he was way before Francis Bacon, about 200 or 300 years before Francis Bacon. So then I went back and I read carefully about Francis Bacon, and I found that Francis Bacon credited this method to Al-Haytham. And so in medieval Europe, he was honored as the second Ptolemy. And he's got it all right here. Those 7 steps are absolutely essential for the scientific method. And then there's Al-Razi, who, this is a truly amazing statement here. Well, he was critical of the Aristotelian view of a single world, but he explores the notion of the existence of a multiverse in the context of his commentary on the Quran verse, all praise belongs to God, Lord of the worlds. And he raised the question of whether the term worlds in this verse refers to multiple worlds within this single universe or cosmos, or to many other universes, or a multiverse beyond this known universe. He rejects the Aristotelian view of a single world in favor of the existence of multiple worlds and universes, a view that he believed to be supported by the Quran. We'll come back to that later. Fortunately for us, even though we're in the Dark Ages, this Gerard of Cremona moved to Spain in order to translate many of the Arabic texts into Latin, and he stayed in Toledo for the rest of his life, and he translated all of these texts, about 24 other key works. Here's his translation of the Almagest. And if you look up in the Encyclopedia Britannica, it says, in a single generation, most of the key words of ancient astronomy became available to the West, which was very lucky indeed, because as a result of this great body of critical work done by Islamic scholars building on the Greek heritage while Europe was going through the Dark Ages. When Europe emerged from the Dark Ages, it had a head start. And this enabled Copernicus to come up with this cosmology where the Earth moved around the sun rather than vice versa. And the timing was just right, of course, and it took off. And this was the beginning of modern science as we know it, and the first step in modern cosmology. So it's very easy when you just displace the Earth and put the sun at the center. Here's the Earth moving around, and here's Mars, and you can see how you can easily get these backward motions. So it's all very simple. Now the second step in modern cosmology I referred to already, which was Einstein's general theory of relativity, published in 1916. And there's a very counterintuitive result of general relativity, which is that the universe has no center, but all observers see a spherically symmetric expanding universe about them. That's not at all obvious, but it's a direct result of general relativity. And in this theory, Einstein showed that there are three possible geometries for the universe. So Einstein managed to tie together matter and energy and space. And he showed that you can get three possible geometries, and they depend on the ratio of the mean density of the universe to the critical density. And the critical density is the density required to just make the geometry Euclidean, which is sometimes called misleading, rather misleading, a flat universe. Okay, so if you've got the critical density, then we define things by this parameter omega. And omega is just the mean density over this critical density, okay, which is just the density which would make things flat or Euclidean. So therefore, clearly, omega is equal to 1 in a Euclidean universe. If omega is equal to 1, the universe is Euclidean. The angles of a triangle add up to 180 degrees. On the other hand, if the mean density is greater than the critical density, then omega is greater than 1, and you have this spherical or elliptical geometry, and the angles of a triangle are greater than 180 degrees. On the other hand, if it's less than 1, the mean density is less than the critical density, omega is less than 1, then the angles of a triangle add up to less than 180 degrees, and you've got a hyperbolic or saddle state geometry. So people have been trying to find out which geometry we have for the universe ever since 1916. And this is the breakthrough that was made in 2000 by Boomerang, which I'll come to later. Now, you should also remember that E equals mc squared, so as far as gravity is concerned, energy has the same effect as mass. So there are three important parameters. First of all is how much energy is there in the normal matter we have, sort of matter we're made of, protons and neutrons and so on. We call it baryonic matter. So omega baryonic is just the density in baryons divided by the critical density. How much is there in non-baryonic matter? We call this dark matter. Should be called transparent matter, actually, but dark matter sounds a lot more catchy title. So that's the density in non-baryonic matter over the critical density, and then how much is in dark energy. So you need to remember that this parameter omega is very important, and it's equal to 1 if we have a flat universe or a Euclidean universe. So the third step in modern cosmology was one I referred to already, Hubble's discovery of the expanding universe in 1929. And he was looking to fainter and fainter galaxies. Okay, galaxies getting fainter as we go along here, and that means that their distance is going up, or their redshift, because the universe is expanding. If they're moving away from us, the light gets redshifted. It's just a Doppler shift. Okay, so the wavelengths get stretched out, so they're redshifted. So higher and higher redshift as you go further and further back, and this was the velocity. And he found that there was this relationship in which velocity was proportional to distance, which showed that the universe obviously is expanding, and the slope is just equal to velocity over distance, which is called Hubble's constant. And then an expanding universe leads directly to the idea of a hot Big Bang. This was Lemaitre's, I pointed out there had to be a primeval atom. In 1931 he pointed out that the universe must have started out very, very hot. Okay, now I'll be showing that we can look back in time about 13.8 billion years to an era long before the formation of any stars, planets, or galaxies, and that at that remote time the universe was remarkably smooth. There were no structures at all. It was incredibly smooth to about a part in 100,000. No variations in density anywhere. Okay? So it was very uniform and very smooth with only tiny fluctuations in density.
Imagine the universe as a bowl of cosmic soup. When Tony Readhead talks about a smooth universe, he means that if you dip into this bowl anywhere, you get essentially the same kind of spoonful. It's the same consistency, same temperature, same cosmic background radiation, all blended together in the cauldron of the Big Bang. Of course, that was 15 billion years ago. Now the universe is lumpy. There are galaxies and stars and planets and croutons. So the interesting question is, how and when did the universe become lumpy? One possible place to look for an answer is at the oldest lumps in the universe, the oldest croutons. And for that, you need a time machine.
Fortunately, we do have time machines in astronomy, and they are telescopes. The sun is 8 light minutes away. Because of the finite velocity of light, it takes time for the light to get to us from the sun, and nothing can propagate faster than the speed of light. So if the sun were to go out, to disappear, to stop radiating at noon tomorrow, we wouldn't know about it for 8 minutes. Okay, for 8 minutes we'd go on happily thinking the sun was still there. Now, of course, telescopes as time machines, I think this is a fantastic, notion, and it's really one of the most wonderful things about astronomy, that the universe is constructed that we can look at it this way. And it's pretty amazing. If you look, now here's the great nebula in Orion. I showed you that little, that central star on the sword of Orion, which you'd see by the naked eye. Looks through a telescope, it looks like this. It's 1,500 light years away. So we're seeing that light today that was actually emitted 1,500 years ago. And of course, it's reciprocal. If there were anybody living in this area of the Great Nebula Orion, and they were looking at Earth, it's the same light travel time, they would be seeing the Earth as it was 1,500 years ago. They would not see us here today. They'd be seeing it at the time of the sack of Rome by the Vandals. Okay? So you look back in time with telescopes. The center of our galaxy is about 25,000 light years away. Okay? So if anybody happens to be on a planet looking at the Earth from near the center of the galaxy, they're going to see what was going on here 25,000 years ago. A great ice age had begun. This is all ice here. The woolly mammoth distribution is shown by the light green here. There's this beautiful, we were obviously creating beautiful works of art. This Venus de Resempoi, I don't know how to pronounce that, probably is 25,000 years old. And if you were looking back from the center of the galaxy at the Earth, you could imagine that you'd see scenes like this. Here are the woolly mammoths, people painting the woolly mammoths in caves in France, a hunting party killing a woolly mammoth. There are lots of woolly mammoth skeletons found with very clear evidence of having been killed by hunters. If we go to 10 million light years, then it's pretty interesting for this part of the world, because 10 million light years ago, so 10 million years ago, this part of Saudi Arabia here was savanna, okay? And this part up here of the Sahara was temperate broadleaf evergreen forest. That's what would have been going on in the northwestern Sahara 10 million years ago. I just like this notion of how you go back in time, with telescopes. 62 million light years, okay, you're going back to the epoch of the dinosaurs. 183 million light years, Archaeopteryx, or the beginning of Gondwanaland. This is how the continents were arranged 200 million years ago. Okay? All of this one major continent called Gondwanaland. And this is how they've drifted over the last 200 million years. And 600 million years, you're going back to these very early shelled creatures like trilobites. This is the Hubble Deep Field. This is the deepest field photograph image ever taken of the sky. The closest galaxies here are about 500 million light years away. The most distant galaxies are very far away, and as you go towards them, as you go to fainter and fainter galaxies, you go through the epoch of the solidification of the Earth's crust, the formation of the solar system, and you can go all the way out to the faintest. The most distant object that's been found is right up here in this little region here, and if we blow it up and we sort of bring up the contrast, this is thought to be a galaxy 13.2 billion years ago, just 480 million years after the Big Bang. And that's the most distant galaxy that we've seen so far optically. And this other stuff that's faint here is just noise in the detector. It's not actual sources, it's just noise. Beyond this, if you take away the noise, that's what you see. Optically, we get no signal from that epoch of the universe. And these are called the dark ages. But radio astronomy holds the key to looking back to much earlier epochs, long before the first galaxies and stars. Because radio astronomy gets signals from much earlier than those first galaxies and stars. So here's a timeline, the age of the universe, and here's an optical telescope, and you can go back through all those epochs we just discussed. And by the time you get back to just 1.5, 2 billion years after the Big Bang, this is what galaxies are looking like. They're not looking like galaxies at all. They're just little embryonic, little baby galaxies. They're beginning to form, but they are not yet proper galaxies. This is what they look like a little bit later. But you can't go beyond this 400 million years after the Big Bang. There's the dark ages, and there's the Big Bang. But if we change to radio telescopes, then there's this epoch just 380,000 years after the Big Bang, which gives out the radiation that we can pick up with radio telescopes. And in fact, that is the microwave background radiation. It's the oldest visible signal from the Big Bang, the oldest visible signal from the most ancient light existing in the universe. These photons were produced 13.8 billion years ago. They've interacted with nothing since then. So we're actually looking back with a radio telescope all the way 13.8 billion years and seeing the universe just as it was 380,000 years after the Big Bang. That's an image that we made with our telescope in Chile. So, but there's another thing, which is actually, as this radiation propagates towards us, the universe is expanding. And so radiation gets stretched out. It gets redshifted. And it gets shifted from the visible into the radio. This was very bright. It was about 3,000 degrees. It gets shifted into the radio. So let me just go back to that and tell you what I'm going to do here, because most often when you look at cosmology, you see this kind of a timeline, a sort of linear timeline here, which is useful for most things, especially if you're doing optical astronomy, because you go back to this epoch, you can't go further back. But if you're interested in getting right back into this epoch here, you really need to have a different scale, kind of log scale. So that's what I've done here. Let me just quickly go through that. So what I've done here is to blow up that very early epoch now. Okay? So now this is about 13.2 billion years ago here. That most distant galaxy would be out here. And I've stretched out that we've seen in Hubble. I've stretched all the rest out here so we've got time, place to look at it. And this shows you how long this was after the Big Bang. So that's 380,000 years. That's where the microwave background comes from. But we think that in this very early phase here, there was an inflationary epoch where the universe suddenly expanded by a tremendous amount. And all sorts of exciting things happened then. And then over the next 380,000 years, you've got these oscillations in the plasma there. And as the universe expands, it is cooling. And by the time it cools to 3,000 degrees, before 3,000 degrees, the electrons are free from the nuclei. You've got a plasma, and they scatter light. They scatter radiation. So it's like a thick soup. You can't see into it at all. It's like a fog. But after the universe has cooled to lower than 3,000 degrees, it becomes optically thin, and you can look all the way back, as we do with our radio telescopes, to this epoch. But we can't penetrate this veil here. Okay, so I'm just showing you here that the electrons are scattering the photons, and the light gets redshifted to radio, as I showed you, and then we can pick it up with a telescope like the Cosmic Background Imager, or the Planck telescope, which is still observing. Now, this looks like a big stretch, so it would be nice to give you some reason to believe that we can actually look into this epoch and know what's going on. And there's one very nice thing that you can do, which is that at 1 second after the Big Bang, things are very hot, but the light elements start to form. So basically, you start getting hydrogen transmuting through nuclear reactions into helium and deuterium and lithium. And so the Planck satellite has made very accurate measurements, and the results are shown here. And this pink strip shows you the allowed range of densities in normal matter, protons and neutrons, that's allowed by the Planck satellite. And these blue strips here show you up here for hydrogen, the abundance in hydrogen, here the abundance in helium. And the blue strips show you what optical astronomers have observed from the primordial, from looking at stars that they know only has the stuff that was produced in the Big Bang and nothing else. And then the green shows you what theory predicts, standard Big Bang nucleosynthesis. And the beautiful thing is you can see that it's easy to choose a value for the baryon density where you can satisfy all of these different constraints. So we have absolutely no doubt that we know what was going on just 1 second after the Big Bang, because Big Bang nucleosynthesis works so beautifully. In fact, we can go much further back than that now because of the Large Hadron Collider. So let me just get rid of some of these. Because the Large Hadron Collider showed us exactly what's going on at the electroweak unification. They predicted and they found the Higgs boson. Okay? And that gives us a lot of confidence that we know the relevant physics all the way back to 10 to the minus 11 seconds after the Big Bang. We're very confident that we can go that far back. This step here is the next one, is very interesting. The relevant physics is still speculative. And then beyond that, we don't know. It's highly speculative. So the thought is that you have this epoch of inflation here, and gravity is a quantum phenomenon, and so it turns out that gravitational waves are produced in inflation, and so the gravitational waves are going to propagate, and then they're going to interact here with the photons and the electrons, just as you're going to get the radiation produced. And they're going to leave a signature in the radiation. It's a kind of polarization called B-mode polarization, and that's what the BICEP2 team may have detected. Originally, we're pretty confident they have, but it's not entirely clear that they have, but they may have detected that. Well, that's what we looked at with our quiet Q and quiet W, and we only got upper limits. We didn't detect anything. So, of course, if that's true, if they have detected this signal from here, basically what that does is it removes this veil. You can now probe with a signal all the way back to this very early epoch. So that's what I mean by back to the beginning in cosmology, really back to the Big Bang itself. And then at the very end of my talk, I'm going to talk a little bit about back to the beginning in experimental radio astronomy, because this epoch is also very interesting because we go through the dark ages, the first stars, and the epoch of reionization. This is now the new frontier. So there are two frontiers, this one which is very new, and this one which people have been trying to reach for some time. So we have different types of instruments that are trying to address each of these. Okay, now this is a projection of the Earth. It's called a Mullwhidder projection, and it's an equal area projection. And if you do the same projection of the microwave background on the sky, the whole sky has been observed in microwave background, that's what you get. This is about the right color, because it's about a 3,000 degree body, and that's the color of a 3,000 degree body. And that's what it looks like. It's incredibly smooth. Now that's actually real data, okay? That's the real data. And there are some critical problems with the standard Big Bang theory. And I'm not going to go through all of them, but I'm going to just talk about three of them. One is, why is the universe expanding? The standard Big Bang doesn't tell us that at all. Another is called the horizon problem, which is because the temperature is the same over here to over here, and it's the same to within 1 part in 100,000. There's a problem with that because the horizon size, after 380,000 years, light can only have propagated over a distance that's as big as that little circle there. We know this radiation is from 380,000 years after the Big Bang. So that means anything that's separated by more than that distance couldn't have communicated. So how does it know it has to be at the same temperature? That is a big problem. That is a deeply troubling question for physics and cosmology. And then there's the origin of structure problem. What gave rise to galaxies, stars, and planets? Well, the inflation theory, and I'm not going to go through it in any great detail here, but the inflation theory basically resolves these problems. And they think that back at 10 to minus 35 seconds after the Big Bang, or at 10 to minus 35 seconds, there was a field, and I'm not going to go through it in any detail, but basically just show you this one thing here. You can work out the density and the pressure, and under the conditions that they're talking about, these factors are very small, so that you can see that the pressure is equal to minus the density. P is equal to minus V, and the density is equal to V. So the pressure is equal to minus the density. That means you've got a negative pressure. And a negative pressure is like a repulsive gravitational field, and that makes the universe expand. Now this comes straight out of the physics. This is Einstein's Geometries theory of relativity, which basically gives you a very similar answer. I won't go through that. But the beauty is, here we at last have a mechanism which we think works for producing the expansion of the universe. So this is what they think happens, that the universe started off as a very, very small, the region of the universe we know started off as a very, very small region and then expanded by a huge amount and then went on expanding much more slowly. So this is the Big Bang. Now, since the early 80s, our view of cosmology has changed dramatically, and a lot of this has been due to CMB observations. There are three types of energy. There's dark energy, dark matter, and ordinary matter. And we can measure these to very high precision, as you see here. So the general view, the general picture that we have, or we had on the universe until about 15 or 20 years ago, was that galaxies were these highly isolated systems with huge regions of totally empty space between them. That was the general picture. It's what it looks like. It's what you see. But this is completely wrong, it turns out. This is not what is going on at all. And the person who first figured out that it was wrong and realized that things were very different was Vincent van Gogh. Okay? Because with his artist's eye, 100 years before the scientists saw anything, he's put all these wonderful swirls in the sky. Okay? He's imagined all of this stuff up there. Right? It's fantastic. This stuff is all dark matter. He didn't know that it was there, of course, but the fantastic thing is what he painted here is very, very much more accurate, a picture of what's actually going on out there in space than what we see optically. So this is how dark matter does its magic. So here's a lump of dark matter with slightly denser regions, the darker regions. And it'll collapse a little bit under its own gravity, but it can't get rid of its angular momentum, so it can't collapse much. But then our amount of material, our baryons, are photons and protons and electrons are superposed on that. And so here you see the photons and the electrons are the purple and the protons are the green. Okay, and they start to collapse into the deep potential wells of the dark matter. And after a while, the dark matter stops collapsing because it can't get rid of its angular momentum, but the normal matter keeps on collapsing because it can get rid of angular momentum. And after about 400 million years or so, those things turn into these galaxies. So that's how dark matter produces. We would not be here. Our galaxy would not exist were it not for the dark matter in our galaxy. Now, we haven't detected the dark matter yet, but I'm confident we will detect the dark matter within the next 15 years or so. That's probably even pessimistic. The dark energy is a much bigger problem, because if you try to calculate the dark energy and you write it down on the back of an envelope, you get it wrong by 120 orders of magnitude. This is the worst theoretical prediction in the history of physics. There's clearly something very badly wrong with our physics when we get a prediction wrong by 10 to the 120. Okay, so I told you that the microwave background is very smooth, but it's not completely smooth. And the people who told us that it couldn't be completely smooth were these people, Peebles, Sunyaev, and Zeldovich, because they said, obviously it can't be completely smooth, because if it was completely smooth, it would still be completely smooth today. There wouldn't be any galaxies or stars. We wouldn't be here. So it's not completely smooth. There must have been tiny fluctuations in density, which built up and led to gravitational attraction over the years and formed galaxies and stars and so on. And so they had thrown down the gauntlet to us observers, and we started looking for fluctuations in the microwave background. We started using this telescope at the Owens Valley Radio Observatory, and at the end of 10 years of effort, Cambridge and Manchester were dominating the large angular scales, and Caltech was dominating the small angular scales, and we got a very stringent limit on fluctuations, very, very stringent limit. And it was so stringent that it told us that if all the matter in the universe was baryonic, then galaxies couldn't possibly form in 500 million years, which we knew they were doing. So basically, this is a table from our paper, and there's about 4 dozen different cosmologies there. And you can't read the lines, but I'll tell you what the individual columns are. So first is the total energy, then the energy in baryons, the energy in dark matter, dark energy, Hubble's constant, and the slope of the spectrum. And so all of these cosmologies up here are no dark matter and no dark energy. They have dark matter but no dark energy, and these have both dark matter and dark energy. And then if you put in the limit that we derived on the temperature fluctuations, it rules out all of those models. And if you say you don't want the models to be anything bizarre, if you want to just be a normal vanilla kind of cosmology, it rules out all of those models as well. And you're just left with two models. And if I blow them up, this one here fits the Hubble constant. And you see that's the right Hubble constant. So it's saying that 3% of the energy is baryonic, in baryonic matter, 17% is in dark matter, and 80% is dark energy. So we published this in 1989, and we actually had the results pretty well right. But we didn't jump up and down and say this is what the universe is, because nobody had detected fluctuations yet, and we weren't sure that we were actually measuring something real about the universe. We now know, in retrospect, that we were. So our next experiment, we went to this remote site in Chile, and it's near Bolivia and Argentina, up at 16,000 feet. And at that time, there was nothing else there. There's many telescopes up there now, but we were the pioneers at the site. So we had to truck in our own diesel. That's our power plant, and our telescope was here. And it was just absolutely wonderful working at this remote site, high up in the Andes, absolutely on our own. It was fantastic. And our students learned a lot about running radio telescopes, and they learned an awful lot about maintaining diesel generators. And so this is a picture when we were setting up, and a good friend of mine very sadly died a couple of years ago, Wal Sargent, but we were in frequent communication at this time. And he sent me an email saying, oh, I see you've got a lot of more help up there than we thought you were going to have. And I thought, what on earth is he talking about? And so I asked my student, John Carter, I said, Wal sent me this strange email saying we've got a lot more help than we expected. What's he talking about? He said, oh, that's Josh Bloom, who was another graduate student. He's been taking our pictures. He's a bit of a wag. He's been taking our pictures and photoshopping them and putting them up in the astronomy building at Caltech. So I said, well, can you give me one? Can you send me one? He said, yeah. So this is what he sent me. I assure you, we didn't have that extra help. Okay. It should be sound now. Okay. This is our software writer, Martin Shepard, is playing the Quaker, and is a Caltech undergraduate playing the charango. I just find it amazing that we get paid to do this kind of work. It's just amazing. So when you're up there observing, you look at the night sky, and it really does look like this to the naked eye because it's so dark. There isn't any light pollution. You can see all these dark clouds in the galaxy. It's absolutely beautiful. And then you imagine that you've got these photons that are coming to you from 13.8 or so billion years ago. These very photons that were last interacted with anything 13.8 billion years ago, and now they're going to land on your telescope. It's really absolutely amazing. And so the next slide I want to show you, because it just really blows your mind away to think of what's actually happening when you're doing these observations. And so I've got a simulation here that's a realistic simulation of how dark matter forms galaxy clusters. It's taken a lot of hours on a computer to get the simulation. And so what I'm going to show you is starting a very long way away as the photon propagates towards the telescope, how the universe is forming the kind of structures that we see in the universe today. So it starts out very smooth, and then it ends up with these galaxies. So, okay, I've got that. It's coming in the next one. Okay, so this is our telescope, and this was the first image that we made, which is showing you where the dark matter has collected the baryons and the photons in these lumps, which are they're not very dense, but 1 part in 100,000. But within 1 billion years, that turns into something like that. Okay, so here's the movie. So after a night of observing with my students, we're driving down. None of us can believe that we actually get paid to do our hobby like this. It's really wonderful. So here's an image that we made of the sky. These are false colors because of the radio image. But basically what we do is we take an image like that, and we basically break up the radiation into the large blobs, and we put them over here. So these are large structures, and the small blobs. This is kind of like a histogram of how much stuff is there on large scales and how much stuff is there on small scales, right? And this is the theoretical prediction that the theorists told us we were going to find things would fit, and that we were very skeptical about. So that's what we were going after. And this beautiful result came out in 2000. And Andrew Lang was the leader of this, along with Paolo Diamandis. And Andrew Lang was a very, very much loved and treasured colleague of Jean-Louis Chameau and me at Caltech. Died very tragically 4 years ago. But this was a spectacular result that was directly a result of Andrew's genius. And the beautiful thing about it is the blue curve is the theorist's prediction, and the red points are the fit. None of us thought that the theorists would have this right, and they did. It's pretty amazing. And because of the position of this peak here, it told us that the universe, the geometry of the universe is flat. They got this omega parameter that I told you about. It's 1 to within 10% or so. So that's precision cosmology. And from between 1929, when Hubble discovered the expansion of the universe, until 2000, when Andrew and Paolo published this beautiful result, astronomers and physicists had been absolutely killing themselves, and many, many careers were invested in trying to figure out the geometry of the universe. And here they nailed it in this beautiful paper. So we were all absolutely stunned. It was just fantastic. And this was the beginning of precision cosmology. So 2000 is a very important year in cosmology. And it was helped by these wonderful detectors, TES spiderwebs, made by Andrew and Jamie Bock, his close colleague. Jamie's the real instrumentalist, and Andrew's the scientist who's driving this. Well, we were observing, of course, also with the cosmic background imager, and I'm not going to belabor the point, but make 2 points here. Our results are shown by the blue crosses here. They're on smaller angular scales. Andrew got this peak, you see. Ours were looking on smaller angular scales, which is off to the right here. And the amazing thing is, if we just take our results and we try to fit the model and vary those 6 parameters I mentioned, we get this red curve here, just from those CBI points alone. But if you take everything else, Andrew's results and so on, and exclude the CBI data, you get the black curve. So it's fantastic that these different experiments constrain things so beautifully, and we got the same results so beautifully. And there you can see what we would have got without dark energy. And you can see if you don't have dark energy, there's no way that fits the CBI points. Okay, so now this is the WMAP satellite, which was at this point called the second Lagrangian point, which puts the Earth, Moon, and the Sun in the same direction, and so the satellite can look out here without being interfered with by radiation from the Earth and Moon and the Sun. And Planck has been doing the same thing, and these are the Planck results, and I'm not going to go through them. I mean, you can see the precision here, so we really are in the era of precision cosmology. Well, if you look, this is the density in baryons, and it's 4.8%, and the density in cold dark matter is 25.7%, and there's pretty small uncertainties. The slope of the spectrum, we didn't talk much about that. The dark energy is 69 plus or minus 2%. And then the age, the Hubble constant is this figure here, and the age in gigayears is 13.8 gigayears. Now you can also do polarization observations, and so if you've got an oscillating electron, it radiates like that, and then if the electron sees radiation from all sorts of different directions and you can break it up into these different multipoles, it turns out only this one, the quadrupole, is the only thing that produces polarization. You can see why it does that or how it does that here. So you've got radiation from this hot region coming over here, being scattered by an electron to the observer. And if you break that radiation up into a component along the line of sight to the observer and a component perpendicular. After scattering, there's no component along the line of sight. And so basically, you can see how this radiation, which starts off unpolarized, gets turned into polarized radiation if you've got this kind of quadrupole pattern. Okay, and there are two ways of producing a quadrupole pattern. There's one where you can produce it by pressure waves, and that produces this kind of pattern. And there's one where you produce it by gravitational waves which squeeze and stretch space, and that produces this kind of pattern. And this kind of pattern is the one that we're looking for because we're looking for gravitational waves from the very early universe. Okay, so I don't know if Jim Carrey is very well known here, but he's a comic actor. And I was rather surprised when Andre Linde told Jamie Bach, and Jamie passed it on to me, that Andre Linde said, "You really must watch Jim Carrey on B-mode polarization." We thought, what on earth is he talking about? And so this is a film that Jamie Bach gave me of Jim Carrey and Conan O'Brien.
I haven't spoken to you in a little while. Yeah. What have you been doing with yourself lately? We'll get to the movie in a second, but I'm talking about you, the man. What are you doing?
A lot of things. I've been doing a lot of reading, actually, lately.
Reading?
Yeah.
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 Now, seriously, I'm just curious, and I think a lot of us are. What do you seriously like to read, like just like in the book world?
I'm fascinated with science.
Really?
I'm fascinated with science. It's incredible. Have you heard about the new brain theory?
No. Whose brain theory is this?
It's Stephen Hawking has been...
Stephen Hawking?
Yeah, talking about this new brain theory about the universe and opposed to the Big Bang theory, and they're coming out with some new concepts. It's really exciting.
And you actually read about...
The Iperiodic universe. Have you heard about this?
The say it again?
It's very difficult to say. The Iperiodic universe.
Wow, that's amazing that you're reading that stuff.
Well, the model we have now, Conan, is based on the idea that our Big Bang universe was created from the collision of two three-dimensional worlds moving along a hidden extra dimension. But conceptually, the Iperiodic model is very different. There is no inflation or rapid change happening at all. The approach to collision takes place very slowly over an exceedingly long period of time. It's quite fascinating that the rapid change and very slow change can produce nearly the same effects. The difference results in one distinctive observational prediction, though. The inflationary cosmology predicts a spectrum of gravitational waves that may be detectable in the cosmic microwave background. The Iperiodic model, however, predicts no gravitational waves. Effects should be observable in the cosmic microwave background. And I'm just so relieved by this because I've been... No, really.
Incredible.
I saw... The amazing thing is he got most of it right. So this was us observing in quiet Q and quiet W. We observed for 9 months at 45 gigahertz and 16 months at 90 gigahertz. And our results are shown here. And this is what I would have talked to you about if it hadn't been for the March observations of last year by BICEP 2, which gave us this fantastic spectrum that I've just been telling you about. Why is this so important? Well, it was thought that, for science to be science, you must make testable predictions. You've got to predict something and then go out and find it. And so inflation has predicted that there should be this B-mode polarization in the cosmic microwave background. Okay? And so these people now think they may have found it. And that would be a very convincing demonstration that inflation really did happen, that our universe really did begin with this kind of inflationary epoch. And we know that there's a mechanism for producing that in physics. And so it would be really very exciting and a huge step forward if this were true. And of course, if that is true, if inflation happened once, why would it happen only once? Presumably it can happen many times. And so this brings us to the ultimate Copernican revolution. And Andre Linde introduced the idea of the chaotic inflationary cosmology, or the multiverse, which you will remember Al-Razi was interested in that and interpreted some of the Quran in this way. And so the idea here is that our universe is just like a grain of sand on an infinite beach. Okay, so here you have all these other potential universes, and here we have a little patch which, if you blow it up, has our universe in it, our inflationary universe. And here we can do science inside this little bit here, which is 13.8 billion light years across, because that's the time since the expansion. Light can only travel that far. We can't get any signals from further out. And here we can only speculate. We might be able to extrapolate a little bit outside of that, but not much. So it's a really interesting, period to be in cosmology, but I think there are several things that I'd hope you'd get out of this, but I haven't perhaps said them as explicitly as I should have done. We've managed to measure the energy content of the different constituents of the universe very, very accurately, to percent or so. The baryonic matter, the dark energy. There's no doubt about that, and there are many experiments that show this to be the case. But we have not yet detected the dark matter. I think we probably will, directly detected it with a detector. I think we probably will detect it in the next 15 years or so, and that will be very exciting. The dark energy is a completely different thing. The dark energy looks as if it's a property of space itself, and I can talk about that a bit more afterwards. Basically, the fact that the universe is flat is very, very interesting, because it tells you that the total energy content of the universe is zero. Because it tells you if the universe is flat, if the geometry is flat, it tells you that the negative potential energy of the universe exactly cancels the positive matter density of the universe. So the total density of the universe is zero after inflation. And of course, the total energy of the universe before inflation is zero. So the equation of the universe is 0 equals 0. Energy before is equal to energy after. And inflation provides this wonderful mechanism for producing the universe that we see. Okay, so let's see. I want to leave you then with the idea that, from this part of the talk, the idea that we've got these two epochs that we're very interested in studying, this very early epoch that we may have got to. And then just very quickly at the end here, talk about this new frontier that we're looking at here. So there are a number of experiments that's attracting some of the best young physicists around the world, and very small experiments, very inexpensive experiments can actually address this and do fundamental work just the way we did back in the 60s. So I think we've re-entered it. It's a renaissance in low-frequency radio astronomy. And this is an array built by Greg Hallinan at Caltech. It's just 256 dipoles. You can see how simple they are. Here they are being put together by undergraduates. And the whole cost of this array, with all the electronics and everything, is under $1 million. So it's not that expensive a proposition. We would love to have one of these in Saudi Arabia as well, because there are many reasons why you would like to do this in California and with a place at the same latitude on the other side of the globe. Thank you.
Let me bring the gifts. One of the slides that you showed was of an early Arabian astrolabe.
Yes.
And so we're pleased to present you with your own hard copy.
Oh, thank you. How wonderful.
Okay. So
that's beautiful.
Yes,
thank you very much.
Oh, thank you. It's when you and your students were driving down from the Atacama Highlands, you mentioned that you found it hard to believe you got paid for doing this stuff, and indeed, in WEP, I feel the same way. Thank you for that remarkable tour of the origins of the universe through the words of Virginia Woolf and the visualizations of Vincent van Gogh.
Thank you very much.
That's actually the second time in the Winter Enrichment Program that Starry Night of Van Gogh has been shown. Dora dos Santos, in a lecture on imagination and creativity a few days ago, showed the same thing.
I guess there's a lot of us who can't resist it.
Yes. So we're going to take a few questions. I just want to announce, before I forget, that a bus will depart from the top of the stairs at the exit of Building 20 to take people down to the harbor, where the astronomy group the astronomy self-directed group will be happy to lead amateurs in some stargazing this evening. I haven't checked what the sky conditions are, but they're generally quite good. So any of you who wish to be on that bus, please do meet. A question on that?
Yeah, thank you for your nice talk.
Yeah, okay. So yeah, we can move into questions for
So just back to the scale, when you showed the scale from the Big Bang till now, and you said about the baby galaxy. And I think, so you showed something growing up till the galaxy that we have right now.
Yes.
And you said about the expansion of the universe. So do you think it will expand more and more till one day it will stop and degrade?
Yeah, that's a very good question. And it's a question that has puzzled people ever since the work of Hubble, since he discovered the expansion of the universe. And so that was, in fact, one of the things people were trying to find out in trying to measure the geometry of the universe. Because obviously that depends on the density. And if the density is high enough, it's actually eventually going to turn around and collapse again. So that would be the case where you've got an elliptical or spherical geometry. But it looks as if the density is right at 1, or very, very close. We now have to, it's within a few percent of being 1. And if it is 1, it'll actually go on expanding forever. Okay? It has to be a little bit greater than 1 in order, but if it's a tiny bit greater than 1, it takes a very, very long time. We're talking about hundreds of billions of years, but eventually it would collapse again. But since it's very close to being flat, it looks like we think it's an infinite universe actually because of that.
Okay, thank you.
Excuse me.
other questions.
Thank you for the informative talk, but I have a question about something you talk about in picking signals from the Big Bang. It's known that we come from the Big Bang. So the signals that we get, I'm sure we don't get them directly from the source of this Big Bang as much as they're bouncing off objects from the space and then they're coming back to us. I was wondering, how does that affect deciding the age of that signal?
Another great question. Yes. Indeed, that would be a worry. If the photons could be coming and then they could get scattered and do that sort of thing. I think that's your question. Is that correct? Yes. It turns out that once the electrons have combined with the nuclei back at 380,000 years after the Big Bang, once the temperature falls below 3,000 degrees and you turn from a plasma into atoms, the universe becomes optically thin, and a typical photon could travel many, many times across the universe without bumping into anything. Of course, some photons do, because we see them and that sort of thing. But the number of photons that are actually scattered or collected by anything in the universe is tiny compared with the number that just go traveling back and forth. So I can't remember when I last did this sum, but I think a typical photon can travel 20 or 40 times through the universe before it hits anything. So the basic bottom line is that the density in the universe is so low that only a very tiny fraction of photons hit anything, and the rest just goes streaming straight through it. So the majority of the photons that we pick up in our telescope are the ones that just come straight through and haven't hit anything else. So we do know exactly what the time is.
And when you say photons going back and forth, like, how do they turn?
Oh, well, if you had a plasma there, then of course the photons could, hit one electron and excite it, then it would radiate and they'd go off in another direction. So by hitting a charged particle and making it oscillate, you can turn. Or of course, if they hit, a surface of anything like a metal or something like that, and that of course is again because of accelerating the charged particles in the surface of the metal, they can turn. And there's one other thing I should say is that the microwave background radiation itself, the fluctuations are very tiny. They're only 1 part in 100,000, so very hard to see. But the actual microwave background itself is quite bright. It's 3 degrees. So when you switch on the television, especially in the old days when we used to have to search around and you saw all that snow on the screen, about 1% of those little flecks were actually from the microwave background. So it's quite detectable.
Thank you very much.
Yes.
Thank you, Professor. Please, could you explain, is the speed of inflation so much higher than the speed of light?
Yes, it's very, very high. The expansion of the universe it was known to be much greater than the speed of light anyway. And that was before we got the inflation, which is an even faster expansion. So yes, that's what happens. So what happens is a very tiny region of the universe inflates, and it inflates much faster than the speed of light. And so you start off with a very small region which is all in thermal equilibrium, okay? And so that's why it's all at the same temperature, because it's such a tiny region of space. But it gets expanded much faster than the speed of light till it's many, many light travel times apart. And that's why, you know, a photon coming from over there in the sky is at the same temperature as a photon coming from over there. They're separated by about 200 light travel times if you didn't have inflation. But with inflation, they actually started right next to each other.
Yeah, but what would Einstein say to that?
Good, lovely question. Thank you. Yes. So Einstein's theory of special relativity, of course, says that nothing can travel faster than the speed of light. What he's talking about is propagation of signals, okay, within space. Here we're talking about space itself expanding at faster than the speed of light. Yes.
Yes.
So some of Einstein, just to answer, finish off that question, which is a very nice question, Einstein introduced a cosmological constant in his theory. And depending on what the value of the cosmological constant is, and many people think that this dark energy, which is doing all of this expansion of the universe now, is Einstein's cosmological constant. So he actually had a mechanism in general relativity for actually producing this kind of expansion in space.
So my question was more about how you map the cosmological microwave background. So when you look at the maps of the cosmological microwave background that you've shown, you see something that's more or less homogeneous in every direction. But from what I understand, when you look at the sky as Planck or WMAP directly sees it, you see it completely dominated by the Milky Way and nearby sources. So my question is, how do you remove the Milky Way from that? How do you know what's actually the cosmological microwave background?
Yes. Yeah, good question. So it turns out that if you're looking at the total intensity, and if you look at high enough galactic latitude, above a galactic latitude of about 30 or so, then you're dominated by the cosmic microwave background. So in total intensity, it's not a problem. When you start looking and also even if you go to the E-mode polarization, it's not a problem. But when you start trying to go to the B-mode polarization, you need to get down to 100 millionth of a Kelvin, 10 to the minus 8 Kelvin. And at that point, you are bothered by dust in the galaxy. And the only thing I think you have to do is you need to observe at many, many frequencies. And the dust has a different spectrum to the microwave background. So you can subtract off the foregrounds. There are about 4 foregrounds you have to subtract off. So to do the job properly, you need to do the whole sky in about 8 different frequencies to very high precision, and then you might be able to. But it's still not clear that you'll be able to subtract it enough, because the theories that are, there are some people who would argue that that signal from the B-mode polarization is going to be down at 10 to the minus 10 Kelvin or something. And we're never going to get down there, I don't think. So that's why I worry that from our position in the galaxy, we may never be able to detect the Big Bang directly.
Yeah. Thank you for an interesting talk. I just, it's probably a stupid question, but I was always wondering, why are we so keen to know what has happened since the Big Bang?
I don't think it's a stupid question. I think, you know, it's just an interest in knowing how the universe evolved. You know, starting off from these very, very tiny fluctuations in density. I mean, it's nice to think that you know how the universe evolved. So can you start off with nothing more than just fluctuations in density? And so the nice thing about the inflationary theory is that quantum fluctuations, what happened, it's very philosophically beautiful, I think, because quantum fluctuations are, of course, very, very tiny. But inflation inflates by about 50 orders of magnitude or something like that. So you take these very, very tiny, short fluctuations, quantum fluctuations, and they get stretched by inflation to these very large scales, and they give rise to all the structure that we see in the universe. And the amazing thing is, it's one of the things I didn't stress, but I won't try to go back to it. But the amazing thing is that the slope of the primordial spectrum that I mentioned, that Planck had measured, is just a little bit less than 1. It's 0.96 plus or minus 0.01. So it's significantly less than 1. And that's exactly what the inflation people predict that the slope should be, if that's the structure that goes on to form all the structures in the universe. So the whole model fits together very beautifully.
Thank you.
Can I? One more in the 4th row here.
Wait.
when you mentioned that 0 is equal to 0, that the energy before the universe arises is equal to after that, is that what Professor Lawrence Krauss means, that something out of nothing? Is it the same theory he's propagating as well?
So who's
Professor Lawrence Krauss from Arizona?
Oh, actually, it may well be. I don't know if it's what he's proposing. Interestingly enough, I had not thought about that particular equation, and I think most people working in the field hadn't thought about that equation. And then I was at a meeting at the Sternberg Institute in Moscow when Zeldovich, who's one of the greatest astrophysicists in the last 50 years, surprised the whole audience by going up to the board and writing, "This is the equation of the universe, 0 equals 0. And we thought, what's he on about? What's that telling us? And he said, look, if you start with no energy, and if you have inflation so that you end up with an absolutely flat universe, the negative energy exactly balances the positive energy, so you've still got 0. So, but it may be what Larry Krauss is talking about too, I don't know.
Thank you.
Thanks.
Thank you. Okay, I think...
one more question. Thank you for the wonderful presentation. I have a question regarding time. So you were measuring all these signals that were generated long ago. So what's exactly time 0? That's number one question. And the second part would be, what sets time in a unidirectional mode, this time asymmetry?
Okay, thank you. Two very interesting questions. So let me go to the first one. What is the 0 of time? In order to talk about time, of course, you need to be able to agree on a clock, okay? And so one of the wonderful things about the microwave background radiation, which is everywhere throughout the universe, is it gives all of us a clock. It gives, you could say that we will set our clock by when the temperature of the microwave background is such and such a temperature. This is the time. And you can calculate all over the universe when the microwave background was that temperature. So that's, it's given, the microwave background and the way the universe is expanding has given us a beautiful cosmic clock that's very easy to set. And so basically when we're talking about time, we're always talking about time relative to this cosmic clock that we now have in our minds. Before that, it was really hard. But now we know that you can actually set everything, and there's something that's got a time stamp on it. Now, your other question about the arrow of time is a very philosophical one. And it's, we don't really understand, I don't think we really understand the arrow of time that well. I mean, clearly, time moves in one direction, and it has to move in that direction because that's the only way that you get causality. So that's not a very good answer to your question, but I think it's one of those deeply philosophical. I mean, all the equations of physics, of course, are the same, run the same both ways, right? There's time symmetry in physics. And so, but there's something about the way the universe is constructed. And of course it's tied up with entropy as well, because entropy, if you look at thermodynamics, then entropy is always increasing. And so you can use the entropy of the universe, that you can use to set the arrow of time.
Thank you.
Thank you, Tony, for that impressive talk, and I hope you agree that these impressive questions show that astronomy is still very much alive.
Thank you very much. Very good questions.
And,
Thank you.
Yeah.
Thank you.